Hey, this is the in-depth look at analysis of variance. In here, what we're going to try to do is find out how it works. To do that, we need to make sure you understand the main points of class 1, the first class on this, and then why we analyze variance and how it works. And to do this, we'll wind up thinking about effect size just a little bit. Even though we haven't calculated one of these yet, we'll go ahead and skip past step 4 and talk about effect size. But first, there's something a little exciting here for you. Okay, I'm sure nobody saw that one coming. Thanks everyone. We're just going to move on with the test now. Okay, so hopefully you paused there and were able to answer these questions. I'll go over them real quick with you. All right, so last time I said that there are two situations in which you would choose ANOVA. That's when you have more than 2 groups in your study. So if K is greater than 2, in the abstract example, that was 3 music conditions: Mozart, jazz, and silence. And then I said there's another situation where you might have more than one independent variable, and we'll look at that a little bit more next week. All right, so I was talking about how so many levels in a study or an independent variable multiplies the amount of t-tests there are. And while we could use multiple t-tests to analyze all of the possible pairwise comparisons, the reason we don't is that doing multiple t-tests increases the experiment-wise type 1 error. So if you did 3 t-tests and rejected the null hypothesis 3 times, and you used the alpha of 0.05 each time, it would expand to almost 15% by the end of all of those comparisons. So what ANOVA does, as I'll show you today, is it does a single test that holds the overall, what's called the experiment-wise type 1 error at 0.05. So we do it because it prevents type 1 error inflation. Finally, how do F-tests, the ANOVA test, how does it differ from a t-test? Well, only one of these is true. F measures variance, whereas T measures things in terms of standard deviations, specifically in terms of standard error. But other than that, the 4 steps and the logic, they're all the same. And so what we're really learning to do is think about a different data situation. Okay. So let's move on then. We do analysis of variance anytime we have multiple comparisons, regardless of how we get those. We need more than 2 comparisons. We do it to prevent experiment-wise alpha inflation. So the question is, how do we do it? We do it with what's called an omnibus test of variation. An omnibus here just means we test everything at once. Now, the big overall test lets us do one test to see if there's a difference anywhere among all of the possible pairs without telling us where the difference might be. So it's just a broad general, is there a difference somewhere in all these comparisons? And this is kind of how we do it. All right, so if you have a situation with 3 conditions, like Mozart, jazz, and silence, at the end of that, you could lump all the individuals from all the groups together and calculate variance for the whole group. And you would have this giant spread of variability, and you would have to ask, well, where does that come from? And we break it down into 2 sources. Do these scores spread out because the averages are different? So like the average of one group is way over here while the average of another group is over here. That would certainly cause a lot of variance. Or alternatively, is all this variance really due to the fact that people are different from each other? So there's variance here around all the people who were in the Mozart group and all the people who were in the silence group. And all that variance is what's causing variance. Not the fact that the means are far apart, just the fact that people are different from each other. And those are 2 very different kinds of variance. This is caused by your independent variables spreading people out, And this within each group is just people being different from each other. And that's really what ANOVA does, is it tries to tell the difference between those two types of variance. That was really verbal. Let me kind of show you an animation here I did. What ANOVA is really asking is, can you tell the difference between groups based on a measurement you've taken from them? And if you look at these three, you can see that there are three different groups here, but you can't really say where one ends and one begins. There's a lot of overlap. And so if my data from my three groups, jazz, classical, and silence, wound up in there, I'd probably say that I can't really very easily tell them apart. So here comes the animation. Now can you tell them apart? Well, those two still overlap a huge amount, but this one is very clearly different. In an analysis of variance, that omnibus test would say, whoa, there is something happening here. Some of that variance is happening because one of the group means is over here and the other two are over here. So yeah, you can tell something about the groups in this test. So the original would have been non-significant. However, if a study turns out like this, with one of the groups way over here, it would be significant. Here's another way of thinking about that. Those two groups over there, they probably represent the same population. So even though I called them something different, they're probably one single group. If you think about what we did in class, for example, I would say that the people who were sitting at their desk who took their heart rate and the people in the elevator who took their heart rate were about the same. And they represent just a person's resting heart rate. Whereas when we had people do stairs, their heart rate was very different. Now, we did not analyze those as an ANOVA, but if we had all three of those together, I bet what we would find is a significant ANOVA in which the stairs were significantly different in terms of heart rate than over there. Another example is the Mozart effect thing. The original study of the Mozart effect found that jazz and silence produced no changes. They both represent kind of normal spatial ability, whereas Mozart in that original study increased things, and the ANOVA said that it worked. It was probably a type 1 error because other people have not been able to reproduce that effect. And I don't want to accuse people of making up data. All right, so that's kind of how it works. I can run through this one more way here. Notice that the curves here are changed. I want you to think about where they were in the last screen. What I did was I actually left the means in the same place. So let's say this is jazz, silence, and classical, or something like that. See, in this case, the means are the same, but the difference here is that the curves are skinnier. There's less variability because of individuals spreading out, and that allows us to see the little bit of variability that there is within. So here, even though the means haven't gotten any further apart than in my original example, I have more luck telling them apart. And that's because there's less error within the groups. Now, imagine a situation where it's really easy to tell them apart, like that. Here, each group is very, very distinct. In my analysis of variance test would be able to say, yeah, they're all different. Okay, so that's kind of what ANOVA is doing. It's trying to say, can we tell these groups apart from each other? And I've shown you with animation, the main type of variability that we are interested in is the researcher. And that's what's called between groups variability. Here, if you were to take the mean of this group, the mean of that group, and the mean of that group, those three means could be used to calculate a variance only of the means. It would be the sums of squares of those three means divided by k minus 1, the degrees of freedom, so divided by 2. The sums of squares of those three means divided by 2 give us variance. Now, think about what happens to sum of squares. Sum of squares is how far apart are our means. I hit this button here. if my experiment turns out like this, that sums of squares between is going to be huge because there's so much variability among those three means. Here, it's going to be modest because there is some variability. So what a researcher's trying to do is create a situation with very different means. Now, in addition, you want to make sure that these curves are skinny. And the way we make sampling distributions skinny is by having big sample sizes. So the bigger the sample size, the skinnier those things are. All right. So hopefully that makes it a little less abstract. So what we wind up with in analysis of variance. Remember, to analyze means to break something down, and that's actually what we're going to do. So we're going to do a study, and we're going to wind up with 12 participants in a study. And if we look at all 12 of them together, their dependent variable is going to have a lot of variance. And we're going to analyze it or break it down to see how much variance happens because the means are far apart, and then how much variance comes up because of how much error there is within each group. How much random variation is there just from person to person. And our ultimate test of this will be a ratio of how different are the means over how different are the people. In the experiment, of course, wants there to be bigger difference than the means than among the people. Okay. The very final thing that I said we look at today is the effect size. So I want you to think about that ratio. When we talk about how big an effect is in an experiment, we use this thing here. It's called eta squared. So that's the Greek h squared, and it's just a fraction or a proportion. And it says if we look at all of the variability using the measure sums of squares, we look at all of it, what proportion of it is because the means are far apart. And we'll find in a lot of our research that you'll have a small eta squared where about 5% of all that variance is because the means are far apart. Something about the independent variable creates it. Medium means that about 15% of that giant overall variance happens because the means are far apart. And then it's a pretty big effect when you start getting differences between the means that account for 20, 25, or even 30% of all the variability. And what that does then is our F test will do a ratio of how much is between over how much is within. How much is between over how much is within. And so that's what we'll be doing in our next videos. We'll actually see how to go about the process of analyzing variance. Okay? So as a recap, this video is just trying to get into the concept of the omnibus test and what it means to analyze variance into its constituent parts. Variance between the 3 or 4 group means, however many means you have, versus just the within group variability that's just random variance among people.